Okay, so I'm going to show you how to integrate secant and cosecant. In AP Calc, they give it to you as a rule, but for us, they don't, so you just have to know the trick for figuring it out. And it's not one that you would come up with on your own, most likely. But to integrate secant x, what I'm going to do is I'm going to multiply by secant x plus tangent x over secant x plus tangent x. Why I would do that, I'm sure would seem like a mystery. It won't be a mystery for too long. You'll see why it's particularly convenient. But why is it okay mathematically for me to just multiply by secant x plus tangent x over secant x plus tangent x? Because it equals 1, yes. So that's totally legit. So all I'm going to do now, the secant x is in the numerator. I'm going to be distributing that to both of these. So you have secant squared x plus secant tangent. And in the denominator, you have secant x plus tangent x. Question for you. What is the derivative of secant? What is the derivative of tangent? Secant squared. So any idea what would be a good choice for your u? Yes, the denominator. It is. Okay, so the derivative of secant we said was secant tangent. And the derivative of tangent is secant squared. And you still have the dx. And what's fantabulous is that's your du right there. And that's your u. So you have the integral of du over u, which is just ln of the absolute value of u plus c. So it's just ln of the absolute value of secant x plus tangent x plus c. Now, if you were guessing, when we had to figure out the trick for secant that involves secant and tangent, what do you think the trick for cosecant is going to involve? Almost. Cosecant's one of them, and cotangent. So it's going to be a similar process. Have I given you enough time to write down, or need to wait a minute? Okay. Okay, we're just going to multiply by cosecant x plus cotangent x over the same thing. So if I distribute across the top, it'd be cosecant squared x plus cosecant x cotangent x. And the denominator just stays the same. It's going to be a similar pattern. We're going to let u be the denominator. And these are ones you don't use as much, but do you remember the derivative of cosecant? You almost got it. Just put a negative in front of it. Negative cosecant cotangent. And then the derivative of cotangent? Very good. Perfect. You got it. Okay, so that's not quite as perfect as the last one. Do I have the du? I agree, pretty much. I just need what? Oh, I do need a dx. That's true. He's got me. But I do need a -1. So a -1, and the reciprocal of -1 is just -1. So now I've got -1 times the integral of du over u. So it's just -1 ln of the absolute value of u. And is it okay if I go ahead and put that in? Okay. So they could have given you these rules on the formula sheet. They do not. But that is how you integrate secant and cosecant. Okay, so that was finishing off the other notes. There's no additional homework that goes with those two problems, but we're going to get back into the one we just barely started yesterday. Okay. Okay, the main things that are going to be new are going to be these, but some of the problems we do, remember once I teach you a rule, I can mix in any of the rules all together. So the very first two problems that I have are not new to you. They are use substitution ones, but I throw them in because they have a similar form and you kind of have to decide when is it that I need to use the trig substitutions and when do I not. Again, they normally give you the trig substitutions on a test, but in your homework they don't. So on your homework, you are going to have to actually look at this chart and decide what is the trig substitution I need. Okay, but these first ones are just going to be use substitution, but they're the kind where you have to solve for x and dx. Suggestions for what u would be for this first one? Yes. Okay, and then what would du be? Yes. And then you're supposed to solve for x and dx, so what would x be? And we don't really have to do anything on this one, right? Just flip-flop it. So what I want you to do is rewrite this so that it's all in u's and du's. So when it has x squared, I'm going to put in for x u minus 1 squared. What would the square root of x plus 1 turn into? Yes, very good. And dx just turns into perfect. Suggestions on how to proceed. Foil the first part. Sounds good. What am I going to do with the square root of u? Well, foil and multiply. So u squared minus 2u plus 1, if you FOIL out u minus 1 squared. And I'm going to write u, the square root of u as u to the what? And just go ahead and distribute, use power rule, substitute back in. So what is u squared times u to the 1/2? Good, u to the 5 halves. That was just 4 halves plus another half. And then minus 2u to the what? Good. And then just plus u to the 1/2. Okay, use power rule on each one. So this would be u to the 7 halves, add 1 to the power, times the reciprocal. Minus 2, this would be u to the 5 halves, times the reciprocal. And then u to the 3 halves times the reciprocal. What's that? Feels like Monday? Please don't say that. It'll feel better if we keep it Thursday. Okay, so then just substitute back in. I'll simplify that when I do, but just substitute back in u was x plus 1. Plus c. So that was the kind you already knew. But again, it's going to be mixed in with the new kind of the trig kind. Did not need the trig for this one. This one, next one's a little tempting for the trig one because it has 3 minus x squared, which is a little bit like this one. But some of the problems that can be done with trig can also be done with u substitution. Not all of them. So it just kind of depends. I'm going to be able to handle this one, though, with just u substitution. What do you think u would be? Du? Okay. Now, you can solve for x. You can also solve for x squared. It kind of depends. What's the most useful? Okay, so x squared, if I solve for x squared, what would that be? Okay, and I think I may not even solve for that. Let's just see what happens. Okay, because when I look, I'd like to have my du. So what I'm going to do, and again, you can solve all the way for x and all the way for dx and substitute it in and things will cancel and make it look nice for you. But you can also pull things apart. So I can make this x squared into an x times x squared so that I can use the x part as my du, part of my du, and the x squared I can substitute in 3 minus u, and that'll actually make this easier. So I'm going to try that. So I'm going to write this part. How could I write 3 minus x squared? U to the 1/2. And then I'm going to write x squared times x dx. Okay, so I'm just splitting that x cubed into x squared times x. And I'm going to look at this as almost being my du. Okay. Correct. Yes. And that's nice because then all that's du and I've handled it. And I can just substitute in for the x squared, the 3 minus u. Okay, so I'm kind of being particular and pulling stuff off. If it's easier for you to solve all the way for x and dx and substitute in, things will cancel and work out for you. But this is u to the 1/2. The x squared is 3 minus u, and all of that is du. So that's actually kind of sophisticated, pulling apart the x cubed to be how you want it. But once you do that, it's just as easy as the last one. It's just a power rule. Okay, so 3u to the 1/2 minus u to the 3/2. Okay, so this would be negative 1/2 times the quantity, 3, and we'd have u to the 3/2 times 2/3 minus u to the 5/2 times 2/5 plus c. And then we'd have negative 1/2 times 2. I'm going to go ahead and substitute in the u. 3 minus x squared to the 3/2 minus 2/5. 3 minus x squared to the 5/2 plus c. And then you can either distribute the negative 1/2 or not. It's not a big issue either way. If I do distribute it, I'd have negative 1, 3 minus x squared to the 3/2. And then this would be positive. The 2's would cancel. 1/5, 3 minus x squared to the 5/2 plus c.